So hi guys, you are welcome to the video of dynamics, and we all know dynamics is an aspect and an area of physics that deals majorly with forces. So under this topic, we are going to have about 6 to 7 videos, and we are going to be considering Newton's law of motion, center of gravity, center of mass, conservation of momentum, collision, oblique collision, coefficient of restitution, and stuff like that. Talk about rigid body diagram, horizontal oscillation, and inertia. So I think we are going to have to about 6 to 7 of our 2 hours videos of, let's say 6.5 videos for all these concepts and for us to be able to be well equipped in the understanding of this. So the first video we just talk about introduction to forces, because dynamics deals about forces and what actually causes motion. So the kinematics does not talk about what causes the motion. That only discusses about the motion, the state, and when the body is already in motion, then we talk about different factors that are acting on them. So now we are going to start from forces. In this video, we talk about forces, classifications, and if time permits, we can introduce ourselves to Newton laws of motion in this slide. Talk about the application will be in the second video, especially on the second law of motion, which will also carry momentum and collisions. You understand? So, and the third video, I think I'll make that one friction, or what you need to know about frictional forces and stuff like that. So the fourth can talk about center of gravity and center of mass, while the fifth one will be on now rigid body and horizontal oscillation. So let's start with the understanding of the first one, which will be the first slide. I will just make sure I brief it in such a way that everybody can understand. So let's start with force, and let's define force. In early classes, we have defined force as a push or pull. So we can just write that forces is defined. You can say forces is anything. I think this is best. That causes changes, that cause a change in state of motion. So anything that causes a change in state of motion is called a force. So technically, you can also say force is either pull, which you all know when you pull, or push. A pull is like this, or a push is the other way. So pull or push. So now, when we talk about forces, we have types of forces. So talking about the type of forces, forces are having different types. We classify forces into 4 types. We have what we call the strong forces. We have to up our pace. We have what we call the weak forces. We have what we call the gravitational forces. The gravitational forces. And we have what we call, now, many students will tell me now, here I'm not talking about another type of force, which is quite important, which you call electrostatic force. I will explain that, don't worry. The last one I have is electromagnetic forces. Now, not to waste time on this, because most of your exams, you are going to be faced with type of forces and the description of each of them, which I think you might have studied in early classes. Now, to understand this very well, I will classify it in terms of their range, because the way we classify forces depends on the range at which they can travel. Excuse me, in physics, when we talk about strong and weak forces, we also call them short range forces. I just want to make it very fast. Short range forces. And we'll talk about gravitational forces. We talk about long range. They classify them under long range forces. Now, not to waste our time, my dear student, based on this, another important note we can keep on classification of forces or type is that gravitational forces is classified to be, gravitational forces is the weakest. It's classified to be the weakest force. Is the weakest force among all type of. So there's another good note you can keep down. for exam's sake, keep it in mind, gravitational force or gravitation, force of gravitation is the weakest force of attraction we have. So about this, when I say 10 raised to power, well, we can go by their range. I think is also important. Now, about strong and weak forces, I said they are short range forces. In fact, they are radius. Or basically, this weak force you see, my dear students, is under your, when you talk about electrons, nuclear forces. So forces that are responsible for, bombarding forces inside an atom and outside, you're talking about the movement of electron around the atom. You understand what I mean? So when you talk about nuclear forces, we can just write that as a short note. I don't want us to waste time on this because when I start dissecting this, we are going to waste a lot of time. So my dear student, what I'm saying in essence is that when we talk about forces in terms of their strength, we classify them with respect to gravitational forces, which I said is the weakest force. So you need to understand that. So if we want to categorize force with respect to their strength, we use gravitational force as the baseline. So what am I trying to say? We've talked about gravity before, time and time again. So if we say gravitational force is the weakest force, which we have stated. I hope you can still hear what I'm saying. And if you have any issues, I told you can always drop a mail on mosdeacademy@gmail.com. I will attend to you. It's time, don't worry. Now, the second type of force, now I'm going to categorize the remaining type of force or forces with respect to with respect to the weakest force, which is a gravitational force. So I will take the next one, which is a weak force. I hope students are writing the weak force. When we talk about the weak force or weak forces, they are about 10 raised to power 26. I hope you are writing times. They are about 10 raised to power 26 times stronger than the gravitational force. Stronger than the gravitational force. And the next one, you can also keep down a note, is the next one we are going to classify after this is our electromagnetic forces. We talk more about electromagnetic forces when we get to electromagnetic chapter of the syllabus, which you're going to understand what we call electromagnetic under waves and oscillation. We talk more about that. Don't worry, we are taking it a step at a time. So these are said to be about 10 raised to 34 times, or most times we say 36, between 34 to 36 times stronger than what? That's stronger than the gravitational force. And the last type of force I have classified here is the strong force, which is the strongest force of attraction. And this is about 10 raised to power 38 times stronger than the weakest force of attraction. So, my dear students, you just need to be careful about the way we categorize force. In terms of range, the shortest range is what? Is the weak force. In terms of long range, we have two long range forces, which are the gravitational forces and the electromagnetic force. So note that. And when we talk about the range in terms of meter, this is about 10 raised to power negative 8 meter in terms of radius. But all that is not required in the syllabus. I limit myself to what you are supposed to know in terms of forces. So in continuation to that, we can move and talk about the type of force. We can also talk more about force because we said force is anything that change or cause a change in state of motion. Now, another thing we can say is that in continuation to that, because we have to understand a lot of things, this is aspect of dynamics. We are going to face more about forces, what causes force, and what forces causes. I hope you understand that. So about this, we can say forces causes acceleration, because when there is a change in the state of motion of a body, we say that forces causes are another important point, acceleration, which you all know that acceleration is a vector quantity. Everybody knows that. So, and when we say forces causes acceleration, we say the first point I wrote is that forces is anything that causes a change in state of motion. Change in state of motion from early classes you might have studied is called a velocity vector. Change in state of motion is called velocity. I hope you remember that. which is very, very important for us to get to understand. So far, forces causes acceleration. We say we can also conclude by that forces causes change in velocity. Now, about this, what we are trying to say here, my dear student, for understanding's sake, is that when a force is applied to a body, it causes what? Change in state of the motion. Now, when we say change in state of motion, it implies two things. It can change the body in its magnitude, that is the size, or it can also cause a change in motion with respect to its direction. So the change in state of motion of a body is called velocity. Early classes, we say velocity is the rate of change of displacement with time. Yeah, because there's a time. There's always a time. So we need to understand all these shorty concepts, which is always required in the concept or in understanding how forces operate on the body. Now, a good understanding about what I'm trying to say, my dear student, is when we consider a block of mass, as usual, I always tell you there's always a block of mass. Now, this is a block. It is having a mass of small m. A force was applied to this body, as usual. Now, in this direction, my dear students, you can always watch. Understanding of concept is very important. Force is a vector quantity. That is the reason why I am putting arrow on top of that. I'm very sorry I'm rushing. I am very sorry. We just need to cover a lot. Now, because force has what? Force has been applied to this body, it will change the state of motion of this body. Yeah, hence the body will move in this direction. Now, because the force is being applied in the direction of what? Of the mass, of the block of mass M. So what I'm saying is that the only thing that will change here is that the block will change and it will come to another position in the same line. So this type of force that changes what? Only the size. It's only increasing the magnitude of this by changing its state of rest from this point, say, to this point. I hope students are getting that. So what I'm trying to say now is that diagram not done to scale, please, about the size. Let's take. So the force has caused a change in what? In the direction and in its magnitude, because it is only on the same line. The same body is here. The only thing that is changing is what? Its magnitude. So we say velocity vector forces causes acceleration, which is also a vector quantity, which is a rate of change of velocity, which we have discussed under the aspect of our kinematics, rate of change of velocity. So the key thing about force or understanding forces is that forces cause a change in state of rest. Change in state of rest of the body with time is what we call velocity. Force also causes acceleration. When body gain velocity, when velocity change with respect to time, what happens? The body will start accelerating. So this is the way we interpret force. Now, the change in state of body, which we call velocity vector, can actually happen in two ways. Now, when the direction of force that is applied to the body is in the direction horizontal force, which in physics we call tangential force. It's not our first time of hearing this. Anything that is in line with motion is tangential. It's only change what? We have change in what? Magnitude only. Now, another situation, my dear student, can be in the situation whereby we have force that is not applied directly to the body in horizontal. Now, let's talk about what we call perpendicular force, or what you call normal forces in your early classes. Now, about that, sorry, excuse me. Now, about that, we can say if force is applied to a body in this direction, my dear student, you can watch. Now, as the force is not in line, as you can see, this is the force. It is coming like that. Just like what you say, vertical force. Vertical force are normal force. Horizontal force are tangential force. So vertical force are what we call normal. These are called normal forces, or normal force, as the case may be. Now, what happened here, my dear student, is when we have this type of situation, the thing about this is what this type of force that is normal or perpendicular to the surface is not only going to change what? The magnitude. What we see is that what? The more the force here, as the force is what? Is coming in this direction, this thing starts what? It gains velocity, and is what? Velocity with respect to time gains acceleration. As the body starts accelerating, what we say is that as the body starts moving, because it is not in the same direction, because this thing is standing on ground, which is in horizontal position. But when the force is coming normal to it. What you see is that as the body starts accelerating, it starts taking what we call, it takes a turn. And when it takes a turn, we say it has caused a change in direction. So my dear students, my point here is that forces is responsible for two things. One, it can cause a change in magnitude of the body, and also it can cause a change in direction of the body. When forces cause a change in magnitude, such force we call tangential force. And when force causes a change in direction, such force we call what? Normal force or perpendicular force. As you all know, we can get the magnitude of all force. We say total force will be the square of the tangential force, the square of the square root, which we have talked under kinematics, of the tangential force and that of the normal force. So this is the way we relate stores of forces with respect to introduction, which I believe is very important. Now, under the study of Isaac Newton law of motion, we are going to understand more on how mass, the size of the mass, will explain the turning effect of this. Because what we need to understand is if the force is large, or maybe we can just take it in a simple way. Forces causes acceleration. That means the higher the force, the higher the rate at which the something will accelerate, or the body in question is going to accelerate. If the mass we are talking about is now very large, that means what we are trying to say is that what if the mass is large, it will require high force or very high force, as the case may be. You can correct that, better one, very high force for the body to change direction. But if the mass of the body is small, a small force will cause the change in direction. Now, as I try to increase this force now, then the rate at which the body will turn quicker. You can see if the force is being increased, the direction will now be what? It will turn very quick than the way this is. But the higher the force, the higher the rate at which it will turn. And that is what Isaac Newton tried to explain in what we call the first law of motion, talking about law of inertia, which I think under this slide we are still going to talk about it. Because when there is heavy mass, we are talking about heavy inertia. Don't worry, guys, you need to just understand them a step at a time, and that is what I'm trying to do. Sorry about this. Before we go to the next slide, we can also visualize this in terms of 2D. Now, when I say 2D, I mean motion in a plane. You understand that? We've talked about that in kinematics. There is this. Sorry, let me use a better picture for best visualization. So, when I say 2D, you talk about 2 dimensions. So this is the first body now we have, and this is it. Then I want to draw, as usual, I want to draw my motion, which is always like this. Just like the way we talk about in kinematics. Diagram not drawn to scale. Now let me draw a tangent line. Let's say there is a force. Better, we have body is moving tangentially to this part according to what we can see. I'm trying to bring out best stuff that you can see where that's a tangent of direction of a body. Now, when a body is like that, we can now bring out the force. I told you about 2 forces. Now, if the first force is acting normal force, you understand what I mean? This is the body. Now we have, I'm talking about forces direction. I'm talking about forces. The body is acting like this, moving with, sorry, let me it's just understanding, nothing more, nothing less. It's just understanding this very well. Fine. Good. Now, we'll talk about 2 types of forces. We said the first one can be normal and the first one can be horizontal. We have horizontal and vertical force. So if I go by horizontal, vertical force, so that is acting like this to this body. If that is, this is the vertical force. Diagram not going to scale, my dear students, just for us to visualize. And it is acting at an angle of theta to the horizontal force. So if the horizontal force is coming like this, my dear student, diagram not going to scale. Just try to bring out something that is unique for your understanding sake. Now, this is the normal force. This is the direction of the body. This is the initial force that is acting on a 2D plane. I call that the force of F. It's just understanding, guys. Nothing more, nothing less. So don't be afraid. Now, from what we have studied in kinematics, two forces are acting. You can see one is acting like this, and the other one is acting like this. So we can say if we result this force with respect to what we have, everybody knows this is opposite. This will be F sine theta, and the one acting will be F cos theta. So what am I trying to say in a nutshell? I've talked about this in kinematics. The force that is responsible for a change in direction is F sine theta, change in direction. And the one that is responsible for change in magnitude is F cos theta, change in magnitude. Why this is important, my dear student, is because of some questions that we only ask. Oh, sorry about my voice. Trying to work on it. Yeah. Now, some question that we ask us with respect to which force is responsible for change in direction, that is F sine theta, and one responsible for change in magnitude, which we call tangential force, is F cos theta. So I believe you understand this, my dear student. And before I go to the next slide, like I said, let me quickly add a page for more understanding, because we still need to talk about other things before we go to seismic power. Now, let's talk about classification of forces, which is also very important. About classification of forces, we call it classifications of group of forces. Group, not grouped, group of forces. I've given you type of forces, and I said you have a strong force, you have the weak force, you have the gravitational force, and you have the electromagnetic forces. I've explained them in terms of range. I've also explained them in terms of what? In terms of strength. Be careful about a short range that is strong than the weak force. When you talk about long range, we talk about electromagnetic force and the gravitational forces. So I hope students hearing this and are getting it. Now, when we talk about classification of group of forces in physics, we group forces into two categories. The first one is what we call balanced forces. Balanced, yes, balanced forces. And the second type of force is what we call the unbalanced forces. Why I actually create this slide is just to understand this before we move to seismic Newton of motion. I believe it is very important for us to get this one too. Now, about this, my dear student, you need to keep in mind when we say something is balanced or force is balanced, the interpretation to balance forces in continuation to your short note, you say the summation of all the forces acting on the body is equals to 0. That is, when you go for the algebraic sum of all forces acting on a body, the summation of those forces is 0. Such type of force in physics we call balanced force. And for body to exhibit balanced force, we have some example which we can give, which you are still going to learn more as we proceed under this dynamics topic. Now, when body is exhibiting is exhibiting or is under the forces of what we call balance force, what students need to understand under this balance force is that when the total force acting on the body is 0, we say such body, another way you interpret, such body is at the state of what we call static equilibrium. So hope you still remember this under kinematics. When body is at static equilibrium, it means there is no force acting on the body, or the summation of all the forces acting on the body is 0. Please keep that at your mind. So when there is no force acting on the body, another important fact you can write is that the acceleration of the body, which is a vector quantity, is also equals to 0. When we say forces causes acceleration, force is equals to 0. What happened to acceleration is also equals to 0. I hope I'm communicating. So when we talk about another important part is when body is not accelerating, you can say the velocity is also equals to what? The velocity is what? Constant. Please. These are conditions you can bring about balance forces. When there is no force acting on the body is at static equilibrium, the body is not accelerating, the velocity is what? Constant or uniform. Or you say the initial velocity of the body is what? 0. So it is moving with constant what? Velocity. That is also what? Balanced force. Note that. And when the velocity is also 0, and the initial velocity is 0, is either the velocity is 0 or the velocity is constant. So when body is moving at constant what? Velocity, the body is not accelerating. We've talked about that on the kinematics. You remember when you have a straight curve, when you draw a velocity time graph, that is representation on that graph, and kinematics have explained this before. So, my dear students, we don't need to waste time, but before we move on, we are going to talk about what we call the static equilibrium, which is quite important under the balance force. Because to understand balance forces, you need to understand static equilibrium, which is another important part, which I believe you guys must have learned in your early classes. Now, static equilibrium. About static equilibrium, my dear student, is all about a step at a time. We don't need to rush ourselves. Now, we say when the body is undergoing static equilibrium and is acted upon at all, the total force on the body is said to be what? To be what? Initially at rest, or the amount of force acting on the body is 0. We have different applications. For now, we only limit the application to simple applications, which I believe you have an idea on. A very good example is if we have a body that is tight on a ceiling. So look at this. Or basically, let's take it one by one. I don't want it to be now, but I'm still going to talk about these under Newton's law of motion. So let me just take it with respect to time, that is gradually, so I don't rush you too much. I want you guys to get every damn thing under this topic because it's one of the most important. In fact, when you get to university, which you are going to need. Now, about static equilibrium, I've talked about it. We say the summation of forces acting on the body is equals to 0. So note that. Now, another way you can talk about when something is static is what? It is a type of balance force in which the summation of forces acting on body is 0. So, but there are some conditions we can also put into considerations. That is one thing about physics. And about that, you need to understand this. Now, about that, there may be forces acting on a body. The forces might be true. In some cases, the forces acting on the body might be more than 2. What you need to understand is that in physics, there are different laws and formulas. That is why whenever you are in a class like this, which is the online class, you have to keep down a note. You have to write down something that will make you understand it very well. So now let's understand something that when we say something is a static equilibrium, we are saying there is no force acting on it, or the body, you can just keep down a note, the body is being acted upon. The body is being acted upon by a balanced force. So like I said, the simplest form of example I can give to you is that when you tie something up the ceiling, just a simple example for understanding's sake, for now, I won't take it too far. There's a ceiling and there's a block that is tied on top of the ceiling, block of mass M. Now, you know, under this thing, there will be a tension. Tension will act in this point. Don't worry about explanation. I'll give you more on that side. The Newton's law of motion. Weight of this one, which is mg, will act downward. So when we say tension of the body, it's balancing the weight. You can see. So the total force acting here, T minus mg, is equals to what? 0. So such case, you can say it is form of what? Static equilibrium. Do you understand this now? So because tension is balancing weight. These are the two forces. So when the summation of all forces acting on the body is 0, that means you said it's being acted upon by the balance force. And this is what we call static equilibrium. So and how do we do that? Another situation can be you have a block, you apply a force to the block is being pushed by a force, then the opposite force, which is frictional force, balance the force in which you are applying to it. So when the summation of the force and the frictional force is equal to 0, say the body will not move, will remain steady. And when it remains steady, you say what initial velocity is 0, the velocity is constant, or you say it is what exhibiting or static equilibrium. That is in case of what? Two forces. Excuse me, for two forces now. So it is very easy for two forces to balance out each other. Tension is the force in strings or rope, whereby every mass, every body, every system of bodies is what always going to have its weight acting in downward direction. I hope you understand. So about that, we can also have more than two forces acting on a body. So now we have a particular law that explains well about what? About a situation whereby when a body is at static equilibrium and it is being acted upon by more than two forces. This law is called Lami's theorem, which is also important here, which I need to talk about for understanding's sake. Let's keep down a note, which I think is important. We can say when a body is under, I think it's better for you to keep this in mind. When a body is under the state, when a body under the state of equilibrium, under the state of equilibrium is under the influence of three forces, comma, the forces must successively represent the sides of a triangle. The forces must successively represent the sides. So when you have more than two, you know, I have explained static equilibrium with respect to two forces, they balance out, then that means they are going to be equal to 0. Now, but when the forces acting upon a body is more than two, so each of these forces can be represented by what? By sides of triangle. This law is called what? Lami's theorem. You can just write this law, the law is popularly called Lami's theorem. Lami's. I know in your early classes, you might have come across this, which is also very important and under the aspect of dynamics. So to understand that, if you've watched the vector video, this is more or less like triangular vector, which we have discussed there. So we say if the first body is moving like this, the second body will move in opposite direction. Then there will be resultant force that will balance the two forces, which is F3. So we say technically that the first force is moving in F1. This is F1 force. The second force is what? F2 force. And the balance force that balances the three force, you can see, is F3 force. So as you can see, F1 force is facing the angle of theta 1. F2 force is facing the angle of theta 2. And F3 force is facing the angle of theta 3. So talking about it in terms of static equilibrium, my dear student, what we're saying is that F1 force, this is this point whereby all the forces are being acted. The first force which we resolve into components is this. As the direction of F1 is going like this. And this is the direction of F2 is going like this. Diagram not drawn to scale. And F3 force is the resultant force, which is balancing that. This is what we talk about when we talk about Lami's theorem. So we say this is F1 force, this is F2 force, and this is F3 force, which is acting like this. And see, so an F3 force is being faced by what? The angle between this and this is. You can, I told you the angle of what? Angle of vector is always the angle between the what vector and the positive x-axis. Watch the vector video to understand. So all the forces are acted upon what? They are at equilibrium because they are acting upon this point. So that is why we say it is at equilibrium, because they are at equilibrium and they are acting, what the forces acting on this body is more than 2. So each of them are at equilibrium, but you can represent them using our what we studied on our vector triangle. Look at the first force, F1 goes like this. The second one comes, the third one is coming like this. So we represent that and say, according to Lami's theorem, we can keep a note. According to Lami's theorem, we can say, so we say according to Lami's theorem that the first force, which is F1 over sine theta 1, F1 is facing the sine of angle of the first one, must be equals to F2 sine theta 2 and equals to F3 sine theta 3. So we've done this more or less on our vector side. We talked about paragonal of vector, which we talked about how to resolve. So if you want to get the resultant vector, this theorem is what we call Lami's theorem, which is more or less like sine rule in mathematics. If you are a math student, you will know better. So keep this in mind, whereby theta 1, theta 2, and theta 3 are always pi minus theta 1. Please note that pi is 180, the other one is pi minus theta 2, and also pi minus theta 3. So be careful about this pi minus if you want to apply this direct formula, because most of the students do make mistake when it comes to numerical from teaching the students. I have cleared that. Another thing you can understand is if you want to use your cosine rule, which is also applicable, which we have explained as well. If you are using that one, maybe you want to calculate side. This is Lami's theorem. But when you want to calculate side, you can just take any two, then cross multiply. You understand what I'm trying to say? Then you use it to solve. But if you want to apply cosine rule directly, and this is the resultant vector directly, you should be careful that the formula you are going to use is just the third vector square. You know that will be the squares of f1 square plus f2 square plus twice f1 and f2, then cos theta 3. Now I'm using plus. Normally, if I apply the cosine, we should have been minus. But if it is minus, my dear student, then something like this will come out. Because you need to know vector. Watch my vector video to understand. From mathematics, angle on a straight line is 180 degrees. So if angle on a straight line is 180 degrees, this will be what? Pi minus what? Pi minus theta 3. And that is what I'm talking about. What is pi? That is like saying 180, because some of us are not used with pi radian minus theta 3. So that is, then you can see what is our cos 180, cos at the second quadrant. My math students can tell me that the cosine at the second quadrant is what? Negative. So minus times minus is what one is 1 to plus. So if I'm using theta 3, I'm going to use plus. So that is why we give the formula in this way. So keep it in mind when you are doing triangular vector. I've talked about this and how to understand it in details on the vector. I told you before you start anything under this topic of physics, there are some things you need to watch. The first thing you need to watch is you watch the basis of calculus. Some of you might be wondering, how did I put calculus on that physics video and not in our math channel? It is because it is needed to understand everything I'm doing. Then after the basis of calculus, you watch the basis of vector. And after vector basis, you watch, you now start introduction to physics. You follow the, I'm going to release a video on how to use the page efficiently. You understand? For now, we are still doing uploading. With time, we are going to give all videos in physics, which are going to be on the channel. So let's move on according to what we have here. Now, I also need to understand that when we talk about this is what where we stop about classification of my group forces. Now, when you say unbalanced forces, I don't want to open another slide that we don't write too much of note. What we are saying is what the total sum of forces acting on the body is non-zero. That is, they don't balance each other. So these type of forces that are non-zero forces are going to be classified under the size using second law of motion. And that's why we talk about different cases, you understand? We talk about elevator cases, spring forces. We talk about altitude machines. We talk about cases of linear momentum. We talk about lift. We talk about jet propulsion. We talk about elevator cases. We talk about trolley. We talk about different cases which make you understand it very well. And I'll be bringing video for you to see some real experiment video of mine, which I've done in classes before. During those times, we do teach in classroom. So I will show you on how to get all these things and how you can actually understand the concept. About this, I told you, it's always about the formula. But before you talk about formula, you need to know concepts. And that is why you are watching this video. Please do watch them in accordance. And that is why it's on YouTube. We always have the YouTube night to watch and watch and watch and watch and watch. Okay. So with respect to what I'm saying, when forces are not balanced, we say it is what when the summation of forces is not zero, we say such forces are not balanced force, which we are going to classify well under the second law of motion in the second video, because second law of motion is what we take the second video as what as a whole. So we move to the next slide, which is slide 2, I guess. Fine. Newton law of motion. About Newton law of motions, I'm going to classify them into, we all know that it is in 3. So for now, in your early classes, you have learned about how it is being described. The first law of motion is called the law of inertia. Law of inertia. About that, what that law is talking about is, you can quote it. For those of you that what you like to quote according to the law, yes, I know you know how to quote. A body will continue in a state of rest, of uniform motion, or on a straight line, unless compared by some external forces in which it acts otherwise. I can quote many things, anything you want me to quote. If it is physics, I can help you quote it very well. You understand? But it is about understanding, and that is why I'm here. Now, I want to say about law of inertia. Why I'm taking it now, because it's at the advanced level now, no more basic level. So it is basic idea that you need in advanced. So without the basics, you cannot get there. So to write that, you can write that a body will continue in a state of rest, of uniform motion on a straight line, unless compelled by some external forces in which it acts otherwise. But now I said it is called law of inertia. Now, what is inertia? We can just write that. Now, inertia basically is the reluctancy, the way you want it, reluctancy of an object to move, and the reluctancy to stop moving when it is in motion. So now, so the reluctancy of an object to move, or the reluctancy to stop when it is in motion, is what we call inertia. Some people will say it is just a property of a body that resists the change, but that resists force. Yes, very correct. Understand? You are saying when you apply force to the body, we say force can either change what this magnitude of the body, or it changes the direction of the body. When force changes magnitude of the body, I call it tangential force. When it changes the direction of the body, I call it normal force. So these two forces might be resisted. When a normal force is applied on the body, or horizontal force, but the body refuses to change its state of rest. So we say that body is having what? Inertia. Inertia is a mass. So it is just a measure of mass. So if we say every body, there are two types of classification of body, or everybody's. Everybody's simply means large inertia. And what it means is what? When a force is applied to them, what actually happens is what? They actually undergo what? A small change, or a small change in state of motion. I told you it is always good to understand things in your own way. You don't cry. What am I saying? When you are talking about a heavy truck that is having what? Heavy load, that's having heavy mass. What you are trying to say is that what that body is going to exhibit what? Heavy inertia. So when force is applied to the body, The body will not we every force that you apply to the body will only move or change the state of motion with what? It's just a small amount. That is what I'm trying to say. I hope you understand. So guys, be careful about all this stuff because this is very, very important. So small bodies, when we talk about small body, small bodies simply means small inertia. So we say there will be a what? A huge change, huge change in state of motion. So about your law that you are talking about, which is the first law, what I'm trying to say is that if body is what? If body is if body is at rest, or you are talking about body and you apply a force to it, we know force will change the state of motion. So if the body is heavy body, or is having heavy body, or is very large, is what the mass of the body is large, it means that body will have high inertia. In fact, most time we call inertial mass. Please keep that in mind. So, and look at my definition. I said the reluctance of an object to move or reluctance to stop moving. Another thing about bodies that are what? That are actually undergoing inertia is that when they start or when they gain what velocity and they start moving, they don't want to stop. To stop them is what? Another problem because they have large inertia. Well, you are going to understand this well when I get to the aspect of momentum and impulse. You get it very well. But now you can still get it. What I'm trying to say is that look at a cargo ship, for example, which is what you've learned in class 9 and 10. You would be told that if you want to stop a cargo ship or whatever, application of brake will what? You start applying brake at about 200 meters before where you want to park the ship. This is because of what the ship is what? Cargo means load, because the ship is carrying heavy load. So you require what? You require what? A force that what it will that what you have to calculate. If you apply a force to the body, the force will change what we only affect it in a little way. But if you want to make it stop, the body is already moving and is carrying load. You cannot just press brake and it will stop. Automatic brake system like your car, it won't work. You understand? So you have to start applying the brake before about 200 meters before where you want it to stop because they don't stop immediately because they are already in motion. And another reason for that is because of inertia, because of the mass that they are carrying. The same thing happens to all these big buses, the trailers and other things you are familiar with. You can see when the trailer wants to apply brake, they start pumping the brake. I hope you understand what I'm trying to say. They start pumping the brake so that what it will stop at a distance, not exactly where they want it to stop. You can't just apply just the way we apply to our car. It's not the way you apply to everybody. So everybody's having heavy inertia, and inertia is the cause of that, and that is what Sir Isaac Newton is trying to explain. Another application you can look into the first law of motion is talking about if you are in a bus, because these are class 10 illustration, which I believe you might have studied. But for those of us who have, we don't actually have a opportunity to study well in class 10, I'm trying to bring an illustration. When you are sitting or standing inside a bus, for example, inside a big bus in Lagos where we have Moldway, so you're standing there, you now throw a coin upward, and the body is moving at constant velocity. That is, it's moving on a straight line, and you stretch forward your palm. It's not the belief. You can try all these experiments. I have videos on all these experiments I've done before. I'll be sharing in later parts when I'm through with all the concept video. So when you throw it up, you are going to see that the coin will fall back to the exact point at which you threw it. The reason is because the body is undergoing constant velocity, motion on a straight line. And that is the theoretical part of the law. The body will continue in a state of rest, of uniform motion. Maybe you want to write for those that actually don't have it. Now, the law states that a body will continue in its state of rest, or uniform motion. Or uniform motion on a straight line. Unless compelled by an external forces in which it acts otherwise, in which it acts otherwise. So that is that about that, and that is where we stop about the first law. Now, the second law of motion, which is also very popular, according to Sir Isaac Newton, the one you need to know for your lab is just 3 laws of motion. Forget about that. Let's just keep it simple and keep it straight. The second law of motion is called law of unbalanced forces. Laws of unbalanced forces. And about this, when we say law of unbalanced forces, we said forces causes acceleration. Acceleration is unbalanced force. Keep that at the back of your mind, because what the second law is always talking about is just about that the summation of all forces acting on bodies or system of bodies or system of particles is always the product of the mass of the body and the acceleration of that body, or we say acceleration of the center of mass. And yeah, don't worry, when we get to center of mass and center of gravity and the equilibrium in what as a topic on its own, you understand more. So what the second law is just talking about, when forces causes acceleration, acceleration can never be a balanced force, because bodies start accelerating, and when they start accelerating, what you can say the rate will start changing. So it is when you have a balanced force, you say bodies are static equilibrium. When you have unbalanced force, like I've talked about classifications of group of forces, forces are not balanced. Definitely, the body has what starts what accelerating. So, and according to Sir Isaac Newton's second law of motion, the summation of force acting on the body is a product of the mass, and the summation of forces is the product of the mass and the acceleration of center of mass. F equals to ma everywhere you go. At the back of your book, your exercise books, in your televisions, everywhere you go, you see F equals to ma, Sir Isaac Newton. That is the second law. Now, about that, we can also continue to talk about this law and give it another name. Now, if F is equals to ma, let me continue, because this is a level class, we have to understand more than the ordinary level student. We say F is equals to ma. F is a vector quantity. A is also a vector quantity. You can always keep that by placing arrow. Now, from early classes, we have studied in class 10 that acceleration is the rate of change of velocity vector. That means what? Rate of change of dv by dt. Anyhow you want to write it is always applicable. Rate of change of velocity, which is also a vector quantity. Substituting that here, you can have force is equals to mass multiplied by acceleration. I'm substituting the v by dt, as you can see. Now, here, this is another thing which will help us, because we need to understand something now. Now, another thing we need to understand here is that the product of mass and the change in velocity is called momentum vector. This is where we are going. I told you about second law. I'm going to do a separate video about that, but it's going to be a long video, because we need to understand a lot of things. In fact, our application of constraint motion, different type of classification of group of forces, or commonly used force in physics, all these things will be exemplified and will be visualized under the concept. So about now, we just need to have it at the back of our mind that mass and change in velocity of a body. Like we say, we are doing dynamics. We are talking about force. When a force is applied to a body, as you understand now, forces causes acceleration. Acceleration is an example of unbalanced force. Now look at a javelin thrower. Somebody throwing a javelin. The more the force, the more the rate at which the body the more the rate at which the time it will use on in motion. I guess the javelin is having a mass. So, and there will be a time factor. So in fact, we can even bring another thing, which I'm not going to talk about now, which we call impulse. We talk about that under the concept of conservation and collision theory and stuff like that. I think I've talked about that before. So be careful about this. So when a force is applied to a mass, to a body of mass m, there is force causes change in acceleration, which will also the body will gain there will be a change in state of rest, which we call velocity vector. So the body has gained velocity. So when we multiply the mass of that body and the change in the velocity as it starts moving, The product of that mass and the velocity that is changing is called momentum vector, basically called momentum. The body has gained momentum. So theoretically, I can write now that the force acting on the body, oh, sorry guys, the momentum, which we denote by, I would take it as P. Please, you might be denoting as capital M. Yes, it's not a problem in your text material. But in physics, we use it as what? P. Momentum vector, I will call change in momentum, I call it the P for now, is now equals to the product of mass and change in velocity vector. What is change in velocity? That is V minus U. Say the final velocity minus the initial velocity, basic classes. Class 10, you've talked about this. Now, directly, I can now say fine. So if I say, I want to substitute that value, I will now say the force here is now equals to, look at this now, M times dV is now dP over what? Over dt. Now, what can I call this? This is same thing as rate, because of time, of change of what? Of momentum. So the second law of Isaac Newton, which we call the second law of motion according to Isaac Newton, is also the same thing as saying the law of rate of change of momentum. Directly in our A-level questions, Cambridge have come across this time and time again, whereby examiner will ask you, which of the following law is also called rate of change of momentum? It is the second law of motion, which is also called law of what? Unbalanced force. So theoretically, you can even write it in your way. Early classes, you say F equals to mdv by what? dt. I know the V is what? V minus U. The popular way you write it in class 10 is F is now equals to M. You are opening the bracket, change in velocity is V minus U. You close the bra, then you have what? Over T. This is the way you write it then. Yeah, fine. But now you have to take it like this, because I can give you an illustration in terms of momentum and time and ask you to find the force. What you just need to do for me is just to differentiate. Was the rate of change of dP by dt is equals to force. Keep that in mind, because you are going to be using it in solving questions under the numerical section, which is very important. So for now, the second law of motion, which we call law of unbalanced forces, is the same thing as what we say the law of rate of change of momentum. Now, to write it verbally, according to the way he got it, he said the rate of change of momentum is proportional to the applied force, provided the force is being acted in the direction of motion. That is the way Sir Isaac Newton quoted the law. For those that don't have it in class 10, you might actually write it the way I've stated now. The rate of change of momentum, because of time, I'm having less than 11 minutes more to finish this video. Now, the rate of change of momentum, is proportional. I say it's directly proportional to the applied force. It's proportional to the applied force, provided the force is acting in the direction of motion. Now, about this, I have the last one, which I want to quickly talk about. I won't waste time. I think I have to move this up a little bit. Now, about the last law of motion, which we all might have also studied in early classes, there are a lot of applications where we talk about recoil of gun and stuff like that. The third law of motion is called law of action and reaction. Law of action and reaction. About that, let's move this slide up a little bit for understanding's sake and for management's sake as well. So about the third law, which is what we are going to, I'm not going to waste time. Yeah, very good. I think we can write now. So about the third law, my dear student, believe you are still hearing. So the third law of motion is called law of actions and reactions. Law of actions and reaction. So that is the last one we are looking in this video. Now about this is a popular law which everybody might have not or noted in early classes. This is what your teacher will tell you, that to every action, there is equal and opposite reaction. Another way you can say action and reaction are equal and opposite. That's why we say you should do good now because of tomorrow. Karma, the way you say, you call it. Now you can just keep a note, just write actions and reactions. I hope you can see the color of the marker I'm using, or maybe we should change to a red. Actions and reactions are equal and opposite. So action and reaction are equals and opposites is what we talk about. And there are a lot of application about this. So what this law is talking about, I can group it into 3 categories. But because of time and because I still have illustrations to talk about, in fact, I still have one more slide before illustration. Oh my word. So let me up my pace a little bit. Now here, as you can see, action and reaction are equal and opposite. What this law is telling us is what? For every force that is applied to the body, there is always an opposite force. When you apply a force to a body, there's always an opposite force, which always what? Are going to apply in what? In what? To the body. So if we have a forward force, there's always a reverse force. So we can conclude there. I don't want to be writing, you can just put what I'm saying. So to every action, so there are 2 forces now. To every action, there are 2 forces acting on the body. You can say we have the first force is what? The action force, and what? And the reaction force. So always 2 forces are always what? Going to what? Act. Then the action and reaction force are always what? Equal and what? And opposite, which is what you have stated from the law. Just trying to bring them out for understanding. So to understand this very well, let me just give you an illustration for a quick one. There is a grand, there is a grand, there is a grand, there is always a grand, and there is always a block. There is a grand, and there is a block of mass M acting on the grand, which is to be pushed by somebody here, which is to be pushed, a block of mass M. Now, a force is applied to the body in this body. There's a force, oh my word. This is the force. The force was applied to this body, diagram not drawn to scale, in this direction. I hope you can see this. This is the force applied to the body. When the force was applied to this body, there will be a restoring force, which we call the reaction. We what? Will also come like this. In fact, the third thing you can write about this, if you want to write it, I told you I can express it in 3 words. Forces always act in pair. Forces always act in pairs. Sorry about my handwriting, guys. Let's manage it. Forces always act in pairs. Now, the first force is this. Then there will be a reaction, the second force, which I will call F2. Now, you can see the direction of the forces, my dear student. The forces are not acting in the same direction. This is an inward force as is applied to the body, then the other force is coming. So we say F1 is equals to modulus of what? We have negative F2. I hope you understand why negative is coming. Now, negative is talking about the direction of the force. The direction of that force is not in the same direction as the force force. The action force is F1. The reaction force is F2. So now why I'm putting in modulus is because absolute value of any number is always going to be positive. So keeping that at the back of our mind, we can say F1 is now equals to F2. So keep that at the back of your mind, that if a force is applied to a body, they always act in pair. There will always be another force that will balance it. And these applications are numerous and uncountable in physics. We have a lot of them. You have recoil of a gun, action and reaction. Rockets or jet propulsion, action and reaction. In class 10, I know you've learned about all these, but now for now, we are only going to look at the numerical, and there's some tough questions which are going to be associated with A-level and what we are considering in class 12 now. So we just need to understand this very well. And that is why we start from the basis. So this is the way we illustrate or we explain the laws of motion in dynamics and introduction to forces. The last aspect, which is the last slide before the illustration slide, is a commonly used force in mechanics. Mechanics, I said, is an aspect of physics that studies motion. The forces we use in mechanics, which you need to keep in mind for now, is the first one we call normal reaction. Or normal force. Normal reaction. Another force you can keep in mind for now is tension. Tension. And the last force, I'm sorry, I have just 8.5 minutes to end this video. The last force we use is the one we call the weight of a body. So in early classes, class 10, you've learned about all this, but maybe not detailed enough. So for now, we are going to be considering them in details as it is needed for us to understand another important part we call the free body diagram of a body. So a normal reaction, what do we call the normal reaction? It is just a force that acts to balance the weight of the body. Early classes, there is always a grant, like I do say, this is a grant. I'm trying to draw out a grant. Now the body is what the ground is rough. On friction cases, you will understand more about what I'm trying to show you now. I believe you are hearing me. Sorry, I'm rushing. I have to finish up now. So there is a ground, there is a body now on the ground. Now, because of the contact between the body, this is the body of mass M. Because there is a contact between the ground and the body, normal reaction will always act at the point of contact between bodies or system of bodies, as the case may be. So in this situation, as you can see, the block is standing on the ground, which is a rough surface. Now, the weight of a body, we've discussed that in early classes, is always acting downward. That is direction of gravity. We've learned that under the aspect of gravitational forces and Newton's law of universal gravitation. So weight of the body is going to act downward, as you can see. Everybody knows weight is mg. Fine, from class 9. Now, normal reaction, we act at the point of between the contact, now contact body, contact surface of this and the ground. So we say normal reaction is going to act in the direction upward. So keep that in mind. I said under the topic of friction, you are going to get this marks because we are going to talk about cases. So normal reaction, we balance out the weight. Majorly, normal is equals to what? mg. So my point is, there will be what? Normal reaction at every point of contact. So force that acts at every point of contact on the body, you said at the point of contact is called the normal reaction. For now, I will not make it so what? Difficult. Then the last type of force we call tension. Now, tension is the force that acts away from the point of contact. Let it be known. Now, for a good example to explain that in details, let us consider a ceiling. There is a ceiling. As I well, there's a body of mass. There's always going to be a body of mass that is tight, that is hung from a ceiling. According to what you can see here, this is the body, and the body is having a mass of m. Then, because there's a ceiling, don't worry, we'll talk about this in next. Well, we'll talk about it in details in the next video. Where we're going to consider how this thing on a large scale. Now, if you look at this now, away from the point of contact, there's a point of contact between this rope and the block of mass. So away from the point of contact, like I said, there will be what? A tension. So we can say force in strings or rope for now. Force or forces in strings or ropes. So that is what you call tension. So this tension will act away from this body. This is tension T. And you know the weight of the body is going to act downward. That is mg. So tension can also balance what? mg. So which is another important thing. But the last thing I'll quickly talk about here is what we call the free body diagram, FBD, free body diagram. In 200 level, you talk more about this, and 100 level, free body diagram. Now, about free body diagram is one of the most important things you need to learn from now. Like I said, normal reaction acts at the point of contact. Then the overall normal reaction is just the one that takes over, just like you resolve them into magnitude and direction. But for now, talking about free body diagram, it is just a line that is used to represent. It's just an arrow. Let me just put on a note. Sorry, I'm rushing. An arrow used to represent the forces acting on a body. I hope you are there, acting on a body. So keep that at the back of your mind, which is very, very important. So be careful. In this case now, if I want to start with free body diagram of the first one, look at this, guys. Look at this now. To draw that now, I'll just say, okay, we have a body, an arrow. I'll just bring an arrow like this, which is the straight line. Then I have, it is now being tied up by what? Under this, the weight, this is the body at the center here. The weight of this body is acting downward. Then I said the tension of the body is acting like this. This is the free body diagram of this body, which we call FBD. It's as simple as that. The same thing is applicable to this, my dear student. Normal reaction acts in both ways. You can see between the body and the gland, and also like that. So the balance overall, one is just one that we consider. Now look at this, the same thing to this is just the weight of the body is acting downward. Then the normal reaction is balancing it upward. This is the free body diagram of this. So it's not always like that. I can have a situation whereby there is a gland, which is the last situation I'm going to give for now. I told you I will talk extensively on them under friction cases and under other things that we need to know. So just understand this for now. So maybe we have this. So and here we say there is a force that is acted upon on the body in this form. Let me just draw well for next class. We are going to see what I mean by that. And the force is acting upon that body at an angle of, we say two forces can now act. We have the one that we act horizontal vertical force, like what I've talked about, which is the normal force, and the horizontal force, which is the tangential force, which I will resolve to my word. Yeah, which I will resolve into components. So this is the force acting on the body, just for illustration's sake. I hope you are following. This is this. Then it is acting, the force is acting on the body, subtending of an angle of theta between the body. Now, here we have talked about this, that two things we have. I told you there will be weight of the body will act downward. Just relax yourself. And the normal reaction between the gland, we act upward as discussed. Diagram not done to scale, normal reaction. But if you look at this force, I can resolve this force into two components, because this is the force which we've talked about, F sine theta, responsible for change in direction, and F cos theta, responsible for change in magnitude, which you understand. So if I continue like that, and I want to draw the free body diagram of this, what I will draw as free body diagram will be something like this. This is the body. It's acted upon by two forces. Normal reaction is acting upward. This is the body. Then this is acting here. And I also need to let you know that there is another force that is coming and being obtained at an angle of theta, which I will also show. So this is the free body diagram of this simple body in the direction of the motion. So this is the way we do free body diagram. So you can have complex situation whereby maybe a quick one, I still have 5 or 5.5 minutes more. Now a quick one, you can see if you look at this, maybe I have a gland, always a gland. Then I have a block that is placed on top of the gland. In this format, I have this. This is the block and the gland. Fine. Diagram not done to scale. Then here we have a block. Then on top of this, I'm now placing another stick. As is physics for you, you just have to be careful. Then you can see it is placed like this to this point. I want it to slant. Look at this, my dear students. Funny, but it's possible. Now, here, you can see that they are you can now bring out all the forces acting here, because there are different points of contact. This is point of contact, as you can see. Normal reaction we have. Normal reaction we have, which we balance out each other. Normal reaction, right? This is another point of contact, which you can see. You can see, well, which there is another point of contact between the gland and the block. This is another, there will be a normal reaction also acting here. Normal reaction, maybe N1, we call this one, maybe we call this one N2, we call this one N3. You can say, then because normal reaction is acting, the stick is subtending an angle of theta, which you know, to this. Then you can resolve this one into what? Horizontal and vertical. You can see what we are talking about. These are things you need to understand very well. So here, you start resolving your f sine theta, f cos theta. Theta is this one. The other one here will be theta. Then you start talking about free body diagram of each of them. So how do you draw figure diagram of all this type of thing? You start drawing something like this that I have. So illustration about all this will be talked about where in the next class for understanding sake. Weight of the body reacts downward, you know, then upward force, downward force will balance out each other, which is N and mg. You know what I'm talking about. Then the third force, N sine theta and cos theta, everything will be shown as a free body diagram. So this is the way we illustrate that. I'll give a good example and a good questions about FBD in the next class, where we talk about some of the application of second law of motion and as well as third law of motion in details, and also friction. So which will be about 2.5 or 3 hours videos. See you soon. But before that, there are illustrations compiled by students for me to solve. So let's quickly look into it together. I will leave some of them for you to solve. And the first one is a quick one, less than 4 minutes more. Which of the following is a derived unit? We've talked about this one. This is an elementary question. As far as this question is concerned, kilogram, meter, Kelvin are fundamental. Derived units should be Newton. As you know, derived unit contain 2 or more fundamental units. F equals to ma. Mass is fundamental. Acceleration is even what derived on its own. The next question is a diagram. I hope students can see this diagram. In the figure above, 3 forces F1, F2, and F3 is acting on O are in equilibrium. This will be equilibrium. Forget the spelling. The student that made the slide made mistake. If the magnitude of F1s are 10, this is 10 Newton. Let me help you write it. And the magnitude of F2 is 5 Newton. Then find the magnitude of F3. I think I did something like this under Lami's theorem. According to Lami's theorem, we can just bring out the triangle for quick visualization. About that, F1 act like that, F2 act like this, F3 is going to balance out. You need to watch concepts, which I've done. You can't just jump down here and say you want to understand. So F1 is 10 Newton. I hope you are getting this. 10 Newton. F2 is 5 Newton. The angle between the stuffs are 60 Newton, 60 degree, and F3 is what you are looking for. So from paragraph law of vector, I gave you F3 will be 10 square plus 5 square plus 2 times 10 times 5. You are taking the cosine of 60. So directly, my dear student, we can say F3 square, if you have a square, will be 10 squares are 100 plus 25 plus 10 times 5 are, I think, 10 times 5, if I'm not mistaken. 10 times 5 are 50, 50 times 2 are 100. 100 multiplied by cos 60 is 1 by 2, or you say 1 over 2. So F3 square from here, we can say is equals to 100 plus 25 is 125. We are adding with half of 100s are 50. I hope students are still here. The last one will now be F3 square, will now be equals to 125 plus 50 is 175. I think F3 will now be equals to square root of 175. So which you can finish with your calculator. I don't know the answer, but I think it should be, it's more than 13. Maybe 13.8 approximately, if I'm wrong, or 13.2 Newton. You can confirm that. That will be the question answer, and that is correct. So I think we have one more slide. I hope it is not something that is lengthy. Oh, wow. In the figure shows, the figure shows a lot of error when this is being prepared by all these students. Now, the figure shows 2 connected bodies of masses M1 and M2 that is in equilibrium and under gravity. This figure is not even drawn well. The tension in the upper spring is dash. Now, we've talked about this according to what we just talked about, various forces in motion. Tension will act upward, weight will act downward. Tension will balance weight because it's at equilibrium. So tension from what we have studied, we write T must be equals to the weight of the first one is M1G, weight is mg. And the weight of the second one is what? M2G. So what about that? The tension answer is you can factorize. G is common. You can say G open bracket M1 plus M2, which will be the question answer. Or your examiner can write it like this. For beginner, M1 plus M2 bracket G. I hope you understand that. talking about equilibrium and balanced forces. The last but not the least, I've exhausted the time. A 50 kilogram block is dropped on a spring. I think this is the diagram. Where is the block? Let me draw it myself. There's a block here of mass m, my weight is dropped. It will be dropped from a distance of 10 meters above from a spring. If the force constant of the spring, this is not even on what we are talking about, but it's on work, energy, and power is on the page you can watch. If the force constant is 4 times 10 to the power of 4, find the maximum compression of. So as the block is dropped to this, there's a compression. We've talked about work energy theorem. That means work is done by the what? By the spring. Force is applied to cover a distance. No work is done when distance is not covered. So a direct one, guys, I'll just give you illustration on how to do this. So now, what do we know, guys? There is work. Work has been done in moving this. This is at rest. It is dropped at rest. So that means the amount of force that is used to what? To move this out to allow the body at rest to move. Work has now been converted to what? To compression energy, which we've talked about in what? In force spring, we said the energy of force, or whatever you call it, energy in what spring force is half ke squared. Oh, wow. Suppose I'm rushing, half ke squared, or you say half fe, anyone you want to use. Watch the work energy stuff. Work has been done to compress this. So for system of total work done by this body is equals to, you can say this is equals to potential energy and the energy that is used in what? In compressing, just half ke squared. But because it is a balanced force, what happened? We say the amount of the potential energy, mgh, balance at half ke squared. I hope my student can substitute parameter and get the answer. You drop the answer to this in the comment box. Mass is, what is mass? 50. What is g? G is always 10. Gravity is always 10 meters per second square. Given or not given, keep it at the back of your mind. So you just say 50, you multiply by 10, you multiply by the height of 10 meters according to the question, must give you half times, compression is the extension. Force constant, 4 times 10 to the power of 4, multiplied by the extension square. So my dear student, you can cancel double this, then cancel double of this one. This remain 2, this here 1, this here 12.25, this here 100, you can do it in your way. So I'll leave you guys to get the answer to each square. Drop the answer in the comment section. I will be waiting for it. So see you guys soon. I'm stopping here on the second part of the video, which we talked about application of second of motion, spring forces, outward machine, pulley system, elevator cases, pseudo forces, illustrations. Then we are going to talk extensively on all these stuff and how to understand them very well. So I told you we are going to have 5 videos on this dynamics. This is the first one. Don't forget to subscribe, like the channel, share with friends. Bye for now. Thank you.